A 3-ton hippopotamus just entered the Mediterranean Sea. Salinity, 38 parts per thousand. It has 72 hours to live, not weeks, not months, 72 hours. I tracked every biological system as Africa's most dangerous mammal faces an environment that will kill it from the inside out. The mechanism of death is something most people have never heard of. This is Habitat X. To understand how this hippo dies, we need to understand what makes it built for rivers, not oceans. The hippopotamus evolved in African freshwater systems, rivers, lakes, swamps. Water salinity, 0.05 to 0.5 parts per thousand, essentially pure water. To survive in freshwater, evolution built a semi-aquatic specialist. Skin that secretes a red, oily substance called blood sweat. Not actually blood, not actually sweat. It is a natural sunscreen and antibiotic that protects the skin from sun damage and infection in tropical freshwater. Eyes, ears, and nostrils positioned on top of the head. This allows the hippo to submerge its entire body while keeping sensory organs above water. A digestive system that processes 40 kilograms of grass per day. The hippo is a grazer. It leaves the water at night to feed on land, then returns to the river at dawn. But here is the most critical adaptation. The hippo does not drink water. It absorbs water through its skin. Hippo skin is semi-permeable. In freshwater, osmosis moves water from the river into the hippo's cells, keeping the body hydrated. This is passive hydration, no drinking required. In the Mediterranean, this same system becomes a death sentence. Hour 1, 6 a.m. Mediterranean salinity, 38 parts per thousand. The hippo enters the water. The osmotic crisis begins immediately. Osmosis is the movement of water across a semi-permeable membrane from low salt concentration to high salt concentration. In freshwater, the river has low salt. The hippo's cells have higher salt. Water moves from river into cells. In the Mediterranean, the ocean has high salt. The hippo's cells have lower salt. Water moves from cells into ocean. The hippo is not absorbing water. It is losing water through its skin. Every second the hippo remains in salt water, water molecules are being pulled out of its cells by osmotic pressure. This is called reverse osmosis, the same principle used in desalination plants to extract pure water from seawater. Except the hippo cannot stop the process. Its skin cannot close. It cannot become impermeable. Evolution never prepared for this. Within the first hour, the hippo has lost 5 liters of water through its skin. At 3,000 kilograms body weight, the hippo has approximately 1,800 liters of total body water. It has lost 0.3% in 1 hour. That does not sound like much, but the rate is accelerating. Hour 6, 12 p.m. The hippo has now lost 35 liters of water, 2% of total body water. Clinical dehydration threshold, 3%. The hippo will cross that line in 3 more hours. But something else is happening, something far worse than dehydration. Salt is entering the body. The same osmotic pressure pulling water out is pushing salt in. Sodium, chloride, magnesium, calcium. These ions are moving from the high-concentration seawater into the low-concentration cells. The hippo's blood salinity is rising. Normal blood salinity in a mammal, 9 parts per thousand. Current blood salinity, 11 parts per thousand. This is called hypernatremia, elevated sodium in the blood. At 12 parts per thousand, the nervous system begins to fail. At 15 parts per thousand, the heart stops. The hippo is being poisoned by salt, but the hippo does not know this. It feels thirsty. In a river, when a hippo feels thirsty, it simply absorbs more water through its skin. In the ocean, the hippo tries the same thing. It submerges deeper. It stays underwater longer. This makes everything worse. More skin surface in contact with salt water means faster osmosis. Faster osmosis means faster dehydration and faster salt poisoning. The hippo's survival instinct is accelerating its own death. Hour 12. 6 p.m. Water loss, 80 liters, 4.4% of body water. Blood salinity, 12.5 parts per thousand. The hippo is now in moderate dehydration and moderate hypernatremia. The kidneys are trying to filter the excess salt out of the blood, but kidneys require water to function. The hippo has no water. Kidney function is dropping. 80% capacity, 70%, 60%. The toxins that should be filtered out are building up in the bloodstream. Urea, creatinine, excess sodium. The blood is becoming poison. Hour 18, midnight. The neurological symptoms begin. At 13 parts per thousand blood salinity, neurons start misfiring. Sodium is an electrolyte. It controls electrical signals in nerves and muscles. Too much sodium disrupts the voltage gradients that neurons use to transmit signals. The hippo begins twitching, muscle spasms, uncoordinated movement. This is not exhaustion. This is the nervous system shutting down. Hour 24, day 2, 6 a.m. Water loss, 150 liters, 8.3% of body water. Blood salinity, 14 parts per thousand. Severe dehydration, severe hypernatremia. The hippo can no longer submerge. Muscle control is failing. The legs can barely support 3 tons of weight. The hippo floats at the surface, drifting. The heart is in crisis. Cardiac muscle requires precise sodium and potassium balance to contract rhythmically. At 14 parts per thousand sodium, the potassium-sodium ratio is completely disrupted. Heart rate, 55 beats per minute. Normal resting heart rate for a hippo, 40 beats per minute. The heart is beating faster, trying to compensate for thickening blood and failing circulation, but the rhythm is irregular. Arrhythmia. The electrical signals coordinating the heartbeat are misfiring. Hour 30, 12 p.m. Day 2. Blood salinity, 14.8 parts per thousand, 0.2 parts per thousand from cardiac arrest threshold. The brain is failing. At this sodium level, the brain tissue itself begins to shrink. Water is being pulled out of brain cells by osmotic pressure. The neurons are dehydrating. Cognitive function, 40% of normal. The hippo is no longer aware of its surroundings. It does not respond to stimuli. It floats. It breathes. Nothing more. Hour 48, day 3, 6 a.m. Water loss, 280 liters, 15.5% of body water. Blood salinity, 15.2 parts per thousand. Multiple organ failure. Kidneys, complete shutdown, no longer filtering. Liver, failure, toxins accumulating. Brain, severe cellular dehydration, consciousness lost. Heart, 70 beats per minute, severe arrhythmia. Lungs, shallow breathing, 4 breaths per minute. The hippo is in the final stage of hypernatremia. Hour 60, 12 p.m., day 3. Blood salinity, 15.8 parts per thousand. The heart stops. Ventricular fibrillation caused by extreme electrolyte imbalance. The sodium-potassium pumps in the cardiac muscle have completely failed. The heart is no longer contracting. It is quivering. Blood stops circulating. Oxygen delivery to the brain stops. Brain death within 4 minutes. A 3-ton hippopotamus, one of the most dangerous animals in Africa. An animal that kills more humans per year than lions, leopards, and crocodiles combined. Dead in 60 hours, not from predators, not from drowning, from osmosis. After analyzing osmotic pressure, electrolyte balance, hypernatremia progression, and the semi-permeable nature of hippo skin, the verdict is absolute. Can a hippopotamus survive in the ocean? No. 60 to 72 hours maximum. The semi-permeable skin that absorbs water in rivers loses water in salt water. The absence of drinking behavior means the hippo cannot replace lost fluids. The massive body size means enormous surface area for osmotic water loss. The kidneys adapted for freshwater cannot process the salt load of seawater. Evolution does not build flexible systems. It builds precise answers to precise problems. The hippopotamus is the perfect answer to one question. How do you survive in African freshwater? The ocean is a completely different question. And biology does not adapt on a 72-hour timeline. The hippo in saltwater, the gorilla in the desert, the elephant on ice, the penguin in heat. Every simulation confirms the same principle. Specialization is survival in one environment, and death in all others. The most adapted organism is the most vulnerable when conditions change. Which animal should face an impossible habitat next? Write in the comments. The animal, the impossible habitat, and why you think it would survive or die. The most upvoted comment becomes the next episode. Subscribe. The next extreme simulation is coming. This is Habitat X. where geography is just a suggestion and biology is our testing ground.